Hi, welcome back to Learn Maths with Lucy, and today we'll discuss the man who changed the future of mathematics. Let's set the scene. Paris, August 8th, 1900. The best mathematicians from all over the globe are gathered to celebrate a new era. It's the first International Congress of Mathematics of the century. David Hilbert was one of these mathematicians. He was scheduled to speak at the Congress, and little did the audience know this would establish him as one of, if not the most influential mathematical figure of the 20th century. Hilbert set out to pave a path for the future of mathematics, and he did so by presenting a list of outstanding problems, 10 of the 23 that were later published, a challenge to all those who listened in, and they listened. However, more than a century later, although a large number have been resolved, there are still a few which have not. But why? We will look at each problem Hilbert deemed important enough to speak on, and the progress that has been made, if any. These are the challenges that bemused the finest of mathematical minds. The first problem is known as the continuum hypothesis. It asked for proof that there was no infinity between the infinity of counting numbers 1, 2, 3, 4, and so on, and the infinity of all real numbers. Problem 2 is one that Hilbert himself wished to see resolved, as he strongly believed that maths should be governed by a set of known truths, axioms. He asked for arithmetic to be proved consistent, that these axioms that are its foundation cannot, do not, and will not contradict one another. In 1940, the first was shown to be impossible to prove by Kurt Gödel. Similarly, in 1963, it was shown to be impossible to disprove by Paul Cohen. Gödel also showed the answer to the second problem could not be found. However, both these proofs are not generally accepted as definitive answers. He showed it using a system called piano arithmetic, where a set of axioms define the properties of all natural numbers. This was part of Gödel's incompleteness theorem, a bombshell discovery which we are still feeling the shockwaves of today. Gödel showed that if clear axioms are defined, there will still be truths out there unprovable by them, which directly contradicted Hilbert's idealistic future vision of mathematics. Hilbert, as discussed, wished to see mathematics reduced to its basic truths. His sixth challenge was then to extend this into the world of physics, more specifically, the most mathematical branches of physics, such as statistical physics. Some progress has been made towards this challenge, but a general, wide-scale axiomization has not been realized. The seventh problem is as such. Is a to the power of b transcendental for when a does not equal 0 or 1, and b is irrational? A transcendental number being a non-algebraic real and complex number, like Euler's number or pi. An irrational number is simply a number which cannot be represented as a fraction, as a ratio between two integers, for example, root 2. This statement above was confirmed by Alexander Gelfond in 1934, and then backed by Theodor Schneider in 1935, the result being the Gelfond-Schneider theorem. Eighth problem is considered one of mathematics' most pressing issues, the Riemann hypothesis. The Riemann zeta function is defined as 1 plus 2 to the power of negative x plus 3 to the power of negative x plus 4 to the power of negative x, so on and so forth. It is conjectured that the Riemann zeta function is only equal to 0 when the domain is an even negative number, or a number with 1/2 as its real component and a complex component on top of this. Hilbert asked for this to be definitively proven or disproven by finding a value equal to 0 which does not meet these guidelines. This is considered to be so vitally important that it links into the distribution of prime numbers. It is one of the Millennium Prize problems with a $1 million prize set by the Clay Institute. Hilbert's 13th problem is about equations in the format x to the power of 7 plus ax cubed plus bx squared plus cx plus 1 equals 0. The largest exponent in this string is to the power of 7. Hilbert's 13th problem asks whether these 7th degree equations can be solved using only addition, subtraction, multiplication, and division, plus algebraic functions such as square root, a quadratic formula of sorts. Vladimir Arnold and his mentor published a proof of it in the 1950s, but it soon became clear that all they had solved was a variation of the problem, using continuous functions only, functions which when plotted produce a long continuous curve. What many deem to be the proper version is yet to be resolved. Number 16 is named the problem of the topology of algebraic curves and surfaces. An equation containing squared terms is always a conic section of some form. either a parabola, an ellipse, or hyperbola. Hilbert saw a more general theory of the shapes that high-degree equations can form. I must admit, this one is so easy that Hilbert threw it in as a joke, so I invite everyone at home to have a go as a light exercise, and be sure to let me know first when you figure it out. For a warm-up, you could always try it with a small degree of only 8. In his 19th problem, Hilbert asked whether the solutions of regular problems in the calculus of variation are always necessarily analytic. The calculus of variations, aka variational calculus, is a field concerned with optimizing certain types of functions called functionals. An analytic function is a function given by a converging power series. It will have a limit. Essentially, Hilbert is inquiring whether the solutions will always be elegant and smooth. The short answer to this question is yes, as was proven so by Enrio de Giorgi. A solution to the 21st problem was published 8 years after Hilbert's speech. Though later a contradiction to this proof was found, which put it very much in limbo, it is now viewed as partially solved. This problem questions certain systems of differential equations with singular points given, and the system's behavior around these points, called monodromy. Finally, the 22nd problem is about uniformization, another which is believed to be partially resolved. This asks whether every analytic and algebraic curve can be written as a function using a singular value. Though it has been solved in one dimension, work is currently being carried out to solve it in more. And what of the other 13 problems? Well, 3, 10, 14, 17, 18, and 20 have generally accepted solutions. 5, 9, 11, and 12 are partially accepted, and the 2 others are simply too vague to ever truly be solved. These problems represent a turning point. They have inspired many young mathematicians on a journey into the arithmetical world, and they have fought back bravely when poked and prodded by all who came across them. They have led to the realization of new ways of thinking, new branches of mathematics scarcely dreamed about before. It is unquestionable that with 23 questions and 1 speech, David Hilbert altered the course of mathematics, and he certainly deserves his place in history for it.